Are we good? Yeah? Okay. Any questions administratively about the course at this point? Any questions? When's your post-lab 1 due?
Next Tuesday.
Before class. Great. Okay, that's clear. Lab 1, okay. Yeah, not too bad, right? Did you have fun trying to figure out what the, quote, best time for convergence might be? What did you all think? What kind of times were you thinking? Yes?
I got like 15, 40.
Okay, that's pretty precise. I was just kind of looking at the x-axis on that logarithm plot. That's probably fine. I might have said a little bit lower, but that's probably fine. Yes. What were you suggesting? Okay. Yeah. All right. So yeah, I mean, these times I would have said more maybe like 100 or 1,000 or something like that, but that's fine. I mean, 1,500, 3,000. What were you all thinking? Yeah. 1,000. 1,000. Okay. Sure. Yes.
Like when I did it, I got 1,260, but I found it took way too long to run. Like
You really?
yeah, I found it took like 20 minutes to run it. That could be my last time.
20 minutes to run?
Or to like do the to graph
Okay.
it.
Well, what was your minimum time step that you did the range over? Did you do like a really small? Because if you did a very small time step, right?
Yeah.
So you saw I sent you all an announcement, right? Yesterday, or the day before. I can't remember. The days are merging, right? But if you look, I didn't try a very, very, very low time step, right? So if you say, oh, I'm going to do 0.1 seconds, that's going to take it a long time, right? So one of the things, I'm glad we're having this discussion. So one, yes, it's not beyond, I believe that it could be your laptop, okay? My initial hypothesis, though, is that if it took you 20 minutes to run the range, probably started off with a time step that was kind of on the too low side. Yes.
I was talking about like the actual orbit graph where it's doing that. That's what took so long, and I noticed it gets slower and slower over time.
Oh, okay. Another good observation. You were plotting while you were creating the error ratio plot?
No, so I did the error ratio plot, which took like 5 seconds, or it might have been less.
Yeah.
And then I looked at it and found the convergence number to then go plot it to see is this reasonable?
Okay. Yeah.
Because that's what mattered more. I felt like it's
Okay.
in terms of how long it takes to run.
Okay.
It's
Yeah.
not that long.
So if you two things. Excellence. I'm really glad. See, I just look at that. I was just looking at the error ratio plot, right? I didn't actually. I'll be honest. I don't think I put in what I thought the converging number of the converging time step would be back, and then just watched it, right? Because I was just looking at the plot. But yes, you brought up an interesting point. You could go ahead and watch it. That's fine. And if you were calculating these error ratios, and you were plotting the trajectories, then yes, it would take a long time. Okay, because plotting is a very slow process. Okay, so these are good things to bring up and things I didn't mention when we met last time. Okay, other insights from lab 1. Excellent. Okay. Yes, there are people.
I was just wondering if we used a drawn out function, is that basically, what is that like? What's the difference between that and just regular slot?
Yeah, so draw now. There are multiple things in MATLAB, and I'm probably going to mess them up because a lot of times I just try things and it works, right? Draw now, though, right, is going to, it's not going to bring up a completely new figure every time, right? It's going to it'll refresh the figure on the inside, and so that's arguably a little bit faster than typing figure 1, or figure parenthesis 1, right, over and over again. Yes.
Why doesn't it converge to large?
Yes. Now we got to the question, right? So I don't remember. It's one person person sent me a message, and it was like, okay, I don't know exactly what you're getting at here, but then someone else sent me a message, and they shared their plot. I was like, oh, weirdo. Okay, so not the person, of course, right? Just the plot. So it for two months, for 60 days. So Group B does not have this issue. Okay, the announcement went to you. I'll share the announcement with Group B, I guess, after today, so that they know what happened. Right? But I didn't want to confuse them. For some reason, for 2 months, with those conditions, it converges on 0.9939. Okay? And you're like, that's actually pretty close to 1, right? That's not that bad. It's like 99.4% accurate. Okay? But that's just what it lands on. Okay? And that could be some type of numerical instability. It could be the fact that when we say it's geosynchronous orbit, do we really have the exact velocity and initial condition right? Okay, there are a few different things that could be happening here. So this is my hand-waving way of saying I'm not exactly sure why it's going to 99.4% instead of 1.00000, right? But like I pointed out, if you were to back out a little bit and zoom out, so you go to like 10 to the 4th seconds to see, oh yeah, it really is it is progressing towards 1. Okay, then you see that, yeah, okay, it's converging. Yes.
I was first really confused on what converging means. Like I saw that as the time steps got lower, they got to this value. This value was it got to this constant error.
Right.
99,
Right.
But if you got to where I got to, which was somewhere like the 1500s range.
Yeah.
And you plotted you could plot 3 days, or I plotted 10,000 days, and it would always stay around it would just say 1.
Right. Yes, because what's happening, this is a very good observation as well. What's happening is this particular problem. So sometimes it starts low and then goes up, and sometimes it starts high and comes down. And then sometimes it neither goes up or down. What is it, head, shoulders, knees, up? When you're up, you're up, and when you're down, you're down. When you're only halfway up, you're neither up or down. Anyway, so sometimes it goes, what you kind of like is you like it to kind of oscillate about the final solution. That's kind of the most comforting, right, way to look at it. Oh yeah, you're right there. Well, I don't know if it's because you're thinking if it's asymptotic, then does it really ever get there, right? But if it's it's going back and forth around the solution. So anyway, what I would suggest, so at 1520 or 1540, whatever you're saying, that's actually when the simulation was kind of going through 1, all right? But you arguably, to get true convergence in the sense of as I decrease the number of elements, when is the change? When do I no longer see change? You should probably go lower, okay? Because even though it's converging on this 0.99939 or 0.9939 or whatever it is, you probably still want to go lower, okay? So that's something to keep in mind is that, yeah, you can say, oh, I got convergence. I see that I started here and then I start oscillating back and forth. But you could pick a time interval, right, where the point before and the point after it and then the point, there's it oscillates quite a bit. That's not really convergence. That's kind of we got lucky, right? So don't worry, we're not gonna. It's a good, in some respects, I was we all learned something here. Not that it was bad professor, because I should have seen it when I chose 2 months, and actually been this is not the most nicest way to lead everybody off into convergence. All right, but we have a discussion. Any other questions? Any other insights here? Really good, really good. Okay, the post-lab assignment, it's a little bit harder. Some of you are gonna be oh yeah, no problem. That's great. That means you know how to use MATLAB. Okay. Others, this is the time to take it easy. Take it easy. Read. Make sure you understand what's happening in every line. Okay? I mean that. If you don't know what one line means, then type help, that command, in the MATLAB window, in the MATLAB command window, and just read what it means. Okay? Or ask the TA or come and we can talk, right? So like people like asking like, what is draw analogy? You know, these different things, like maybe you haven't seen them before. And there's not always one way to do things, right? Like you could just do like figure parenthesis 1 every single time if you wanted. But then you would have lost the data. So like do like figure 1 and then hold on, you know, like it's just different ways. Any other questions? All right, so we're going to talk about particles some more today, and we're going to focus on boundary conditions, hard walls, periodic walls. Periodic walls are almost like fun. Well, I mean, it's all fun, right? But the math is not super tricky with the periodic walls. The hard walls, we got some vectors that we're going to deal with. We'll talk about drag on particles. So when we were talking about body forces or forces that could act on particles, someone said surface force. I think it was in this session. And I should have immediately said, oh yeah, you could have friction. I think it's something like your friction, and yeah, you could be, I should have immediately said, oh yeah, right, drag, okay? Drag. Now you could argue drag is kind of like a body force, but really it's a surface force, okay? There's a traction vector, there's a shear stress acting on the surfaces of whatever the object is, and it's causing there to be a drag. Now, we'll also do some examples with simulations, and if we have time, I'll show some personal, touching research that's kind of related to this topic, okay? And overall, we're progressing, so you are progressing from particle dynamics to molecular dynamics, but we're going to save the molecular dynamics. And then this lab, this post lab, is about pickleball. So, well, the lab will be about bouncing balls, right? And then the post lab will be about pickleball. And then the next lab will be more of a focus on molecular dynamics, and you have a post lab that the post lab after this one is the one that I think most people get upset about. All right, so we'll try to not, I'll try to give, even for this one, I'll try to give you some clues on how to do these things. In MATLAB, I'll have MATLAB up. You know, go back if you have to, watch the video, like take screenshots, whatever you want to do. I mean, I try not to give the whole shebang, but you'll get some insights. All right, and then really the question today, what you want to walk away with is like, either, oh, I knew that already, which, go you, or, now I know how to think about how a ball or a particle bounces off a ball. Okay, that's pretty much the root of what we're covering today. Because I think you already know about drag, a little bit at least. Okay, so we have a particle and a hard wall. And we had to think, what is the boundary condition? Or, I mean, you have an idea now about what boundary conditions mean in mechanics and materials, right? You're like, oh yeah, at the left, you've got either this zero slope or you've got zero displacement if you're looking at a beam. You know, you could say, oh yeah, the internal shear force is going to be 0 here, or the internal force, right? Because there's a free end, right? So you've done a bunch of math now, so you definitely know boundary conditions in terms of being able to integrate an indefinite integral and then plug in the appropriate value at either end, right? This is going to be a little bit different today, all right? It does, of course, we're going to talk about the math and things. We're going to talk about what's conserved, but it's maybe not just, hey, this is the constant that you put in the definite interval, and then you're happy. And we'll be thinking about elastic collisions. This means that as the particle interacts with the wall, we're going to do our best to assume that there's no energy loss. So some of you will be like, oh, that's a bummer. All right, yeah, I mean, because you want energy loss. Like, what particle doesn't lose energy when it, or what ball doesn't lose energy when it hits the ground, right? Otherwise, a lot of other things would be interesting. Anyone watched, what was that? I think it's an old black and white movie called The Absent-Minded Professor. Disney movie. Anyone ever see this? Anyone ever heard of Flubber? Huh? Flubber? Okay, maybe they made a newer version. All right. But anyway, this scientist makes this material which somehow does not lose energy when it bounces. It kind of actually looks like it gains energy, right? Or just keeps bouncing and bouncing and bouncing, and he puts it on it does all kinds of things. He makes a flying car out of it, for goodness sake. But there's one funny scene where they have he puts it on the soles of a basketball team's shoes, and then like they can jump. Okay. All right. So that's not reality. We're not doing that. Okay. So here is our hard wall, and you might ask yourself the question of what are the quantities that are involved, okay, with this interaction, right? And what's going to be conserved, okay? So here we define the coordinate system, and we say, okay, incoming, outgoing, right? And we have some velocities, some velocity vectors with this interaction, and we know since we're not losing energy, probably momentum's a good one to be conserved, right? You've done that in high school or in physics, where you got the billiard balls that are pinging off of each other, right? And you've got this nice elastic collision, okay? But then someone sticks glue, or you have a clay ball or something, and then you have that inelastic collision, right, where they stick to each other, and blast. Conservation of energy doesn't work, right? But conservation of momentum does. Okay? So momentum being conserved is usually a good assumption. In this case, we'll say that the kinetic energy is also conserved because it's an elastic collision. And with energy, with momentum, we're essentially dividing by mass to be able to look at the components of velocity. Right? So here, the particle is not losing any mass, so the magnitude of the velocity is going to be the same, coming in and going off. And we can also say a couple things about the vertical and the horizontal components. So, for example, if we think of V2 sub x as being the horizontal, right, in the x direction, horizontal component of the outgoing particle, okay, that's going to be equal to the minus of the incoming component, all right, of the particle, right? So we're looking at this, this component, and this in the horizontal direction. And if we look at the y, we can just say that, or the velocity, the speeds, or the coefficients of the j component or the y component, we can say that they're going to be equal to each other. Does this make sense? Yeah? Okay. Now, that's kind of great. Though there are some confounding things that we have to think about. We have to think about where that particle is relative to the wall. All right? So you're marching along using your Euler method or the velocity relay method, right? You're marching along, and you've got to be able to think about, oh, did that particle hit the wall or not? then, right, you have to, like, you would ideally like the particle, right at the instant it hits the wall. You know, that's when you like flip the vectors, you change the velocity, right? The half velocity, whatever you're doing, if you're doing velocity relay, and you know, you're off on your merry way. But in reality, you know, you're probably, depending on your time step, the probability of being right at the interface of the wall in your simulation, well, it's pretty much 0, right? You're going to be some infinitesimal distance away from that wall. And, you know, our particle has some radius to it or something like that. And so there's some complexities. So we're going to use what Professor Singer has expounded upon here. And it's pretty clever. I'll just cite him because I'm not quite sure where he got some of this information, but it's very clever what he does. And we'll go through some of the vector math. Okay, so how do we define a hard wall? So that's maybe, right, we need to know, if we need to know what's happening when the particle comes close to the wall, we need to know where the wall is. So a good way to define a wall is a vector describing its location and a normal vector. And that's kind of weird. Maybe a little bit strange, but it's like, well, it makes sense, you know, because I know that I can define plane and space if I have 3 points. I know I can define a line if I just have 2 points. All right, so here what we're saying is give the position vector can kind of be like a point on the plane, and then the normal vector is going to be some other, it could be at that point, right? But it's got to be a vector that is normal to the plane that we're defining. Okay, so let's see, what does this look like? Well, here now is a hard wall, but you know, it's not just vertical like the last one is. We can pick kind of an arbitrary point on the wall, and that we can call this vector Rw. So R sub W is the position of some point on the wall, and of course that means that this R sub W is in reference to some type of coordinate system. Make sense? But I said we need a normal vector, right? Because this is nice, but you know, now we're saying that essentially the plane of the, so you know, I got a point, right? But I can draw all kinds of planes through that point. So what do? We say, or what we do, we say, all right, we're going to define a normal vector. Okay? And you can see that that normal vector could be essentially anywhere on the wall. And I didn't draw it right on that position vector. Okay, maybe it'll be more clear why in a few minutes, maybe not. Okay, but that's the normal vector. So now we've at least defined the wall. And if because this is drawing it again, all right. The next question is, how do we know if we, now I guess I'm personifying in the first person the particle. I guess you feel a connection to it. I should probably have more like physical to say. How do we know if the particle has crossed the boundary of the wall, right? But let's just say we're on a spaceship and we want to know if we're crossing. So that's kind of a complex question, and there's a pretty clever, I like this, a pretty clever thing that we can do. So the blue particle is the position of, or the blue circle is the particle at some position. And the red is that same particle as if there were no wall. Okay, it's going along merrily, and in the next time step, remember we're simulating in time, this is where it would be if the wall were not there. Okay. So it would be nice if we had some way to know which side of the wall that particle is on, right? Because if I know in the next time step I'm on, or the current time step even, I'm on the other side of the wall, then I need to do something, right? I need a conditional. I need to change something about the simulation. Otherwise, just proceed letting the body forces, drag force, whatever, do their thing, right? And I just march on. So, how do we do that? Well, let's go ahead and define R sub p. All right, and let's define another vector, dw1. Okay, so dw1 is the vector that describes the distance from the position coordinate of the wall that I defined previously, and the position of that blue particle. Okay, and I can define another vector. We'll call it dw2. Okay. Now, dw2 would be a vector that's describing, again, the position or the vector that's describing the distance between the particle and the position of the wall. Yes?
So for dw objects involved to the particle, where on the wall does it connect?
What do you mean by this? Say that again. Where does it connect?
Where on the wall does
It hit. We will get. Okay. Right now, we're just trying to figure out, has it crossed the wall or not? We will get to how it bounces off the wall in a minute. Okay? Just hold on. But first, we have to know which side of the wall we're on. Okay? Because if we're on the other side of the wall, if we've crossed the wall, then we have to do something. If not, then we don't have to do anything. Right? So just hang on for 1 second, because we will address this. Yes?
Will EW1, EW2 be going completely opposite directions? Should RW be directly in between the blue point and the red point, or is it just kind of
So maybe the next. Let me show you the next thing. All right. So what we're going to say, okay, is that dw, all right, is a difference between RP and RW. Now, I get confused. You probably are very smart, and you don't get confused like I do. But I don't like subtracting vectors. I like adding vectors. Okay? So here, I can say that if I put RW on this side, I have RW plus DW equals RP. Can you see that? So RW plus DW is equal to RP. Can everyone see that? Take a minute. Use your brains, all right? Please? Because we're going to do a few of these vector additions. And I know you have all done vector addition at some point in your educational lives, okay? So just stick with me for a second, all right? And if I made a mistake, then you can say you made a mistake, because I did make a mistake in the spring, which I had to fix. So I think I got it fixed, all right? So everyone see that RP or RW plus DW equals RP. Okay? RW plus DW is equal to RP. And I didn't draw another RP over here, okay? All right, but what I'm saying is that you have an RP is like either this particle position here or this particle position here. RP is that position. Okay? So, now, if we're on this side, dig this. The dot product, okay, of dw1 with n, the normal vector wall, the n hat w, is greater than 0. Now remember, what is a dot? Dot product is, AB cosine and theta, right? You remember that if you're trying to figure out what it is in terms of just using the scale, right? The magnitude of vector 1, magnitude of vector 2, and then a cosine, right? And it's defined as being a projection, right, of one vector into another vector. So if you think about the projection, right, I'm projecting dw1 into this vector, and you can kind of see, yeah, it's going to go up maybe, I don't know, here or something. It's going to be, it's going to be less because there's cosine is not 0, right? If you have two vectors and you dot them, and they're parallel to each other, and you dot them with each other, then you got AB, cosine. I mean, I guess, sorry, I should be careful. Depending on what the angle is, it could be greater than either one, right? Because you could have cosine close to 0, and it would be A times B essentially. So it could have much higher. But the idea is that this is being, but this is a normal unit vector, right? So its magnitude is 1, right? So here, like, that means that you just really have A cosine theta, A cosine the angle between these, and as long as cosine is not 0, it's going to be that's going to have a magnitude that's going to be less than whatever the initial A was. Right? Anyway, I'm probably overthinking and over describing this, but you see that this dotted into this is greater than 0. In contrast, and this is now to your point, what do you think happens if you do dW2 dotted with a normal vector? Yeah, it's going to be less than 0, right? Okay, because it's not aligned enough, shall we say, right? It's not within the 180 degree, right? It's not within the 90 degrees, right? That gives us positive. Okay, so this is just a test. I think it's a pretty clever way to figure out if your particle has crossed the wall. Yes.
What is dW2 again? Is that just like if the particle does not make collision?
Maybe I should have said, I could have, if I wanted to be careful, I don't know how to say this. I mean, I could have said like RP sub I and like RPI plus 1, okay, or something. And then I would have been like, and then I would have had to draw the wall in between them, right? So dW2 is just where the particle might, it's just another particle, just another particle, and maybe that's, in our case, if we're doing simulations, that's where the particle would be in the next time step, if there were no wall. Okay, that's from a practical engineering perspective, that's what we're asking ourselves. Is, okay, I'm marching along, and I hope there's not a, it's like I'm feeling, just the particle has feelings, and it's marching along, and then suddenly, I'm on the other side of the wall. I don't know. All right, hitting the wall, okay? So now, let's talk about, I think someone was alluding to this, what happens to the velocity? All right, now, you already got, the vertical wall, just flip the signs, right? It's just like, yeah, that's true, right? But you had to do some type of transformation. Okay, so it's a little more complicated, right? Like, it's not just like, I do like one negative and one positive, and I'm good, right? If I got a wall at an angle, which we're going to be simulating when we do pickleball, right? Anyone ever played pickleball? No? Okay. I played for the first time like 2 Decembers ago. It's pretty fun. I haven't played in New Jersey though. I played in my family. I don't think oh wait, maybe I did play once. Okay. So, how does velocity change after contact? So pickleball, right, well, I mean, tennis court or pickleball court, right, obviously you have the ball bouncing off the ground. That's one type of interaction. But let's say that now we take, like, pickleball paddles and we put them at an angle, and we can say, whoa, the ball comes in, and then it bounces off, right, and where is it going to go? You're, like, hoping that it stays in balance. But it has to go over that. That's kind of what you're going to do, essentially, is make pickleball paddles at a given angle and see the ball go boing, 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 or like, no, it's going to go boing, and then go boing, and then boing, and boing, like that. So it's going to be really fun. I'll show you in a few minutes, all right? But how does the velocity change after contact? So this is going to take a little bit more analysis. Here, we'll say we can draw the two vectors for the input and the output, okay? And we can kind of break it down into a V2, so that's like V2 is like the output velocity. And this is a little bit confusing. Do you see we're before just trying to see which side of the wall we were on. Now we've made an assumption that it bounced off and is at this location. All right. So this V2, maybe a better way to draw it would have been like on this side. Okay. Like it might be better to think of this V2 like that. Okay, instead of the way I've drawn it. Okay, because in a second we're going to talk about how you figure out where you put that particle. Okay, but now we're just saying the particle magically got to this location, which makes sense based on angle of incidence equals, right, angle of exit, you could say. All right. Here, this V2 is going to have a couple components. It's going to have a component that we can say is in the normal direction, and then it's going to have a component that we can say is in the parallel direction of the wall. Yes?
Does RW go to the point of collision with the wall, or is it just...
It's an arbitrary point, right? So here, I still do have the RW, right? But it's not really, it's not the point of contact. At least, it could be. Well, it would have to be, again, you'd be like, what's the probability of that happening? Well, I guess if you like analytically figure it out, you could like make it so, but no, it's just an arbitrary location on the wall. Okay, so now what we can say, all right, is that this velocity vector, okay, dotted with n hat, right? So you see that this is n hat w, right? So that would be giving us a component in this perpendicular direction, right? That's like a projection into it, but it's going to have like a negative sign. Then times that normal vector n hat w, right? That would be what V2n is equal to. Like, and when I do the dot product, I lose my vectorial property of direction, right? I just get a magnitude. But then I take that magnitude and I just put it next to a vector, the unit vector, n hat, and then now I have a vector. Okay? Yes?
You're saying that velocity after contact is always in the normal direction?
What am I saying?
The velocity after contact is always in the normal direction.
I'm saying that there's a normal component and there's a parallel component to the velocity. That's all I'm saying here, right? This is V2n, all right? So this is a vector that is for what happened after it hit the wall, and it's in a normal direction. Yes? Okay, good question. If with this, so this is going to be a negative, right? So let's just work it out, right? So what you're saying is that this is a V dotted with N, so that's going to be in this direction, right? Going down. No, let's see, that has, yeah. So that would be a negative. Yeah, you could argue that there should be a negative, because then it's negative. No, but it's bouncing off. No, there shouldn't be a negative, because this is going to be, oh, this is going to be negative. Yeah, you're right. This has got a negative quantity to it, you're saying. Yeah. Okay. I'll put that in there for now, and then we'll come back. We'll check to make sure that's right. Okay, so then now we have this v2n, and we have this v2 parallel for this vector. Okay? And the v2 parallel, okay, can be thought of in terms of vector addition again. So we have, if you think, okay, this is v2n, okay, plus, or you can think v2 parallel plus v2n will give you the v2. Right? So that's just vector addition. So now, all right, so that defines the normal component and a parallel component for the exit velocity. Right? But we don't actually know where that particle is yet. And so what we do, okay, is we need to do a little bit more vector math. Okay? So here's the wall. Here's a position, all right? And here is, okay, let's put this out. Okay, so this RP now is the location after we went through the wall. RP2 is the updated location due to the wall. All right, and we'll say in this case we're just it looks like we're just mirroring it across the wall. Okay, so this is, so imagine you originally, the particle might have been I don't know, might have been here, but it was coming in kind of like this, and we know it's going to reflect off like that. But this is the location it would have been if the wall had not been there, right? This is going back to what we were talking about. Did it cross the wall or not? So let me just, I'm just going to erase this. Just that's what we're talking about. Okay, so now we have this, again, this dW, all right? And we can think of the R wall. I've moved the position of the wall to be out of our way because there are all these vectors there, right? So this is, again, an arbitrary definition of the wall location or a point for the wall. And we're going to say that we have this RW, all right, plus DW is going to be equal to RP, right? RW plus DW is equal to RP. RPN, all right, so this right here, this vector, the distance from here to here, we can think of as being the DW vector dotted with the n hat times n hat, okay? And I guess to your point that you made earlier, maybe that's where the other negative comes in. Okay. Now, we can also think of RP2 plus this 2 times RPN, right? So the RPN and RPN is going to be equal to the RP. Okay, you see that? RP2 comes up to here, then 2 times RPN gets us to this orange vector, which is RP. So another way to look at this is that we can say that R parallel. Okay, so let's do R parallel, which is this vector, okay, plus the RPN would give us DW. All right, RPN is this vector right here. And we could also say that we have RP2, okay, minus R, or equals R parallel minus RPN plus RW. So if we go ahead and we do some substitutions in here and we do the math out, we can get this as well. Or we can look at it and say, all right, RW, this vector right here, okay, plus RP parallel, all right, which is this vector right here, okay, gets us as this location, is equal to RP2 minus RPN, which is this location here, all right? So anyway, we've done a bunch of different things to describe this RP2. RP2 is where the particle actually is after you've reflected it appropriately through the wall. Yes, sir.
I know I don't think this, but even if we take into account gravity, which is probably as even if you take account gravity as an acceleration, it still wouldn't matter. Like it's still reflected.
Right. So we will try to use a small enough time step, right, where any type of trajectory, right? Yes, I mean it will. It can affect the acceleration, right? It can affect the acceleration, but we're going to say that we're interested in just thinking about a velocity change at this point. Yeah. Yes.
So this is like almost like what you're doing right here is basically going like, so let's say like there's 15 time steps coming up to the wall, and there's one time step like 15 to 16 where it's on the side or on the side of the wall. As it passes, it uses this function once, and it puts in all the data, and then continues to use what it normally does.
That's right. And so it's flipped the velocity. Like if you go back to just the vertical wall, right? It was coming in, and if you have the vertical wall, right, and it's coming in from the bottom, it keeps its vertical velocity, right? But all it's done is it's flipped the horizontal velocity. Yes.
But I mean, like in the case of like, let's say you have something accelerating downwards with gravity.
Yeah.
In this, like passes the wall. If the wall's like at a slant and it passes the wall, it arcs like this. It would.
It's one time step where we essentially are changing the direction of the velocity, and then gravity will start working again. Okay. Yes.
So this works relative to any origin and any arbitrary point.
That's the idea, yes. That's the idea. Good. Okay. So we do need to get going. I'm glad we're having a discussion, all right? Let's talk about how we code this. Okay, so we're going to use MATLAB, okay? And we're going to have to do a few things. One is you have your code just running, right? It's like going through the loop, and you have to add the conditional statement. So that, you argue that can slow things down. If you have to check this every time, right? Does it slow it down a whole lot? For our intents and purposes, I don't think we're gonna notice it that much. Okay, I haven't done a TikTok on this, right, to see how much is a conditional statement. But we are, because essentially, right, we have to calculate this dw, this vector, and then we have to do this dot product of the dw and the normal vector for the wall. Okay, and we're doing now these two things every time, right? So as the ball or as the particle is going through space, every time at least I have to figure out where I am relative to the wall. Okay? And then we're going to do this dot product. Yes?
Does that mean that since our vector components are normal to the wall and parallel to the wall, we're going to, like, no matter how the wall is oriented, we set our coordinate system to where y is normal and x is parallel, and like not like global, not like the absolute coordinate system.
So we're going to use tilted walls too. Okay, we're going to define walls with a theta, with an angle. All right. Again, you have to pick a coordinate system. Should you be wise in the selection of that? Yes. Okay. Yeah. Okay. So then what happens is, all right. Here is our position, all right, before we hit the wall. This is the position after we hit the wall, and you can kind of see, yeah, that looks like a reflection that you would expect. This time I put the vector for the velocity, right, kind of coming off of the particle instead of off of the wall. And this is going to be our new position, and that's where the particle would have been. That 1' is where it would have been if the wall had not been there. And we can start to look at, okay, this is this is going to be our velocity, okay, this VP2N, all right, like that. And this is going to be our parallel velocity, okay, in the code like that. And this is going to be the velocity. This is the new velocity, right? And essentially, right, we're keeping the one that's parallel, right? It's going to keep going in the parallel direction, and it's going to be flipped in the normal direction. And this back there, that was the DW, the displacement vector that we used in the first place. And we're going to use that now to figure out where the new location is, okay, for this vector here. Okay. And we can also think of, of this expression for defining the new location. Okay. So that's the parallel component of the location, and then the actual location. So that is, yeah, so, okay, so I jumped. That is, we're going to get there, right? This is how we code a hardball boundary. Do I expect everyone to be like, oh yeah, that's like, I do this in my sleep? No, right? This is a number of steps, okay? And they do work, right? We know it works because the simulation runs. Okay? And I want to go back and figure out that negative sign. I have to think about that, okay? Because it might be that we have a negative times a negative, which is, I just had to think about that. Thank you for reading that. I think it's right the way it was, because it works, or we had a double negative that knocked itself out. Good. This is the hardball. Now, the trailer is for periodic boundary conditions. All right. Now, have any of you seen this movie? Maybe? Yes. All right. So the arch, let's see if it works. I don't know if it's going to work, but we'll try. Okay. Let's see. Yeah, I got some volume. All right. So I guess, well, the sequel to the sequel, this is a sequel movie, right? And the final, or the next one hasn't come out yet. So there's a cliffhanger about this movie. All right? And one of the enemies, because it seems like by the end of this movie, not to spoil things, there are multiple enemies now of our friend. All right? But one of the enemies has an interesting power. All right? And so you're going to... Whoops. Okay, here we go.
So
all right.
Are you like a cow or a Dalmatian? I am the Spot. It's not funny. Don't do that.
Miles' grades are pretty good. A in AP Physics. That's my little man. And a B in Spanish.
Ooh, okay. Miles, mira, eso es imposible.
I gotta go. Bye.
He's lying to you. And I think you know it.
Okay, so what was I trying to show you there? What in the world were we trying to show? Someone else. Did anyone see the special powers of that other thing? Yes.
The Spot character can cross boundaries at will.
Right. It can jump from one point in space to another point in space. All right, and it can just like travel somehow through that space-time continuum. Actually, just really space continuum. I think it doesn't really have control of the direction of time. All right, so just somehow he goes from one spot to another, but it's in time, of course. Okay. Whoops. So this brings us to the fun periodic boundary conditions. Okay? So these come in pairs. You have one wall and you have another wall. And just like that spot character would go from one like spot, or I guess one whatever pole, wall, okay, boundary, right, to another boundary in another location, periodic boundary conditions act the same way. Okay, so this ball disappears and then it comes back. Right? Want to see that? I don't know how, I spent a little time on this animation, so I'm going to show it to you again. I'm going to show it to you again. Right? How do you do that in MATLAB? How do you do that in a simulation? I can do it in my PowerPoint animation, right? But how do you do that in MATLAB? Okay, someone else. Sarah? Huh?
What is that supposed to represent?
We'll get to the physical meaning of it in a minute, or how you use it in engineering practice in a minute. Okay? But right now, I'm just presenting the idea. Okay? How do you do this? Yes.
So we know how to check if it crosses like a boundary. So when that happens, you change the position and you keep all the velocities.
Yeah, right. That's a good way to do it. Okay? And in our MATLAB code, we're actually going to do something even simpler than that. But that's a very good description of how you could do it. Okay? Yes, Kevin.
Maybe just spitballing, but if you estimate the ball as a particle the second it passes over some x coordinate, you can keep the velocity the same and the acceleration the same, but you just manually transfer position to the ball.
Yeah, I think that's what you were saying. I think good. Well said, both of you. All right. Do you live in any type of periodic system? Yes. Okay, you're nodding your head. What is the system we live in? Yeah, the 24-hour cycle, right? So it's 2 something p.m. It's 3 p.m. Shoot. Okay, it's 3 p.m. and we want to get, and tomorrow we know we're going to be at 3 p.m. again, right? In 24 hours. But 3 plus 24, right, is not 27 in our way of thinking of things, right? It's 3 plus 24 modulo 24, right? So we talked about this a little bit before. So one thing you can kind of do is you can do a modulo on position, right? So if you end up adding, right, and you go past a particular number, and we're just doing this very simplistically for this exercise on vertical walls, okay? The point is that you cycle over and boom, you're on the other side, right? So it's like what we do with time, but now we're doing it with space, all right? We gotta go, because I'm behind, all right? So we can use the modulo operation, okay, to do this. Now, if you want to think of real-world examples, okay, here's one from Professor Bacci, okay, and he's one of the guest lecturers as well that you can watch, right? How do you think this particular simulation that's his group has run is exhibiting a periodic boundary condition? Yes.
When the particles exist from the left, they're then right circle that.
That's right. Okay. Right. We know that we have to conserve flow. Okay. Now, yes, fluids is not a prereq, right? It's supposed to be a co-req, right? For many of us. Although really the amount of fluids we do in this class, anyway. But you got to graduate, right? So that's what's going on. All right. So yeah, we know that the flow in and the flow out, right? They're going to the conservation of mass, conservation of volume, if it's an incompressible fluid. So yeah, so that's this is an example of you could flow the particles right back in and just circulate the system again. So this is one case where spot and this, well, the simulation of blood cells are similar. Another situation where you have periodic boundary conditions is actually in the mechanics side. And we won't talk about this, but for example, if you have a chunk of material, okay, and you're like, oh no, like the reviews last semester for mechanics materials, I was sad at it. One person said, I still don't understand how to figure out the state of stress at a given location in space. It's like, oh, I failed. All right, so here, all right, imagine you know the properties of a material, okay, or the material properties at a given location in space, right? But you know it over a very small quantity. Let's say you know it over a cube, right? But now the actual structure, right, has some width, has some height, right, has some length. I don't know, however you want to do it, right? Width, length, height. If I know the dimensions of that particle, okay, or that voxel, or that cube in space, I can stack those particles in series, okay, if I'm going this way, right? Or I could stack them in parallel, all right? I'm assuming like I'm interested in property of like maybe flow in this direction. But I can use kind of this periodic boundary condition where it's like, oh, yeah, what's coming in, I'm going to kind of assume that's like what's going into this one and what's coming out of that. So you can kind of stack different, it's not exactly the same, but you can kind of stack the properties of these voxels on top of each other to get the overall properties of your structure. So anyway, this is interesting that you can use this periodic boundary condition for real world applications. Okay, drag on particles. Most of you have probably, who's seen this kind of equation at some point? Okay, most of you, all right? If you haven't, it's okay, all right? Fortunately or unfortunately, usually drag force is related to velocity squared. Why is that unfortunate? Because mx double dot plus bx dot plus kx, that nice second order differential equation, that bx dot, like x dot being the velocity, right? B being the damping. Usually, you know, those equations, those ordinary differential equations are nice and linear without like an x dot squared, right? So we can solve those without, you know, just like their closed form solutions, right? That's what you did in your differential equations class. In this case, and in the real world, the velocity, the drag that you have on an object is related to the velocity squared of the object. Except, all right, in the case of laminar flow and a sphere. So laminar flow over a sphere, that drag force is actually 3 pi, the viscosity, the diameter, and the velocity, right? So if you have a sphere of a particular diameter, and you know the viscosity, so this is units of pascals, seconds, or it can be, this is in units of meters, and this is in units of meters per second. Okay, you can figure out what the drag force will be. So, well, we will do some calculations with circular objects, okay, in laminar flow later. But this relationship does not have the b squared. These coefficients are often calculated or often measured experimentally. Okay? But we'll also show you when we do airflows at various geometries, and maybe some of you will do this type of work in ANSYS later, that you can simulate them. and hope that they match what's in the literature. Okay, but we'll show you how to handle those types of problems later. Okay, so the point is, if you have a particle, it can also have drag on it, and if you have a pickleball, like it's kind of like a ping pong ball, it's like a cross between a ping pong ball and a tennis ball, right? Drag could be acting on that as well. Okay, so these are some things to consider from today, or so far. Which quantities are conserved with a hard wall? How do we define a wall? How do we know if we have crossed the wall? What do we need to do to change the velocity? And what do we need to do to change the position? Okay. These are all questions that we've addressed and maybe have a little bit of an idea of how to handle them. Let's talk about what you're going to do in the lab. Okay? So the lab is going to have a ball above the earth, and then there's going to be a flat wall. Right? We're not flat earthing this, right? But this we have a flat wall. Okay, that's how we're right. We can assume that the wall, the earth is more or less, the ground of the earth is more or less flat relative to the distance we're going to travel. Okay? We're going to run the simulation for a certain amount of time and actually take a look. This is one example, but please read the instructions because just for the sake of giving everybody a chance to do a little bit of original work, you know, change the time of simulation if it asks you to do that. And we're going to look at how this ball travels and how gravity acts on it and how a drag force function can act on it. Okay? And this will all be in a tutorial. But to give you a little bit of an idea, all right, here is a simulation. We have, okay, a mass of the ball, and we have a mass of the earth. Okay? The mass of the earth is only important, right, in terms of calculating the gravity that's involved. Given this distance of 100 meters, the gravity is not going to change a whole lot. Okay, that's how high it is above. But when you calculate, you know, when you do the GMM over R squared business, you're going to be using the 100 meters plus the radius of the Earth. Okay, when you calculate that gravity. Okay? But again, that 100 meters gravity's not going to change a whole lot. So here's the radius of the Earth. All right, that's 6,000 kilometers. And then we have plus 100. That's our offset. That's how high off the ground we're starting. This is maybe a little bit overkill, to be honest. But since we just did orbital mechanics, it's kind of like, you know, using the same formulations that we described previously. We can calculate the distance of the particle, and this is, you know, pretty much at any time, but at least initially, taking the magnitude, right, which is the square root of the squares, right, of the components. And so one way to do that is the dot product, and you've seen this already. And then we give it initial velocity. Now, we can think of this as a two-dimensional problem. With the coordinate system here, what are the two dimensions? What are, like, say, with an x, y, z coordinate system? What are the two coordinates that we're really thinking about here? Like their letter names, based on what you see here in the initial conditions. X and z, right? Y is not really doing anything here. Okay, you see that it's 0. So we're saying that z is this height, and x is you've got an initial velocity in the x direction. So the ball starts here, and somehow it magically has some velocity in the horizontal direction. Is that velocity going to change direction? Yes, right? Because you have acceleration of gravity causing it to go down toward the ground. It would be really weird if I put the ball up here. It'd be a really silly, not very interesting simulation. Okay, because then I just keep going. So we have now an x velocity, we know its initial speed, right? We have containers. We're not even keeping track of y. You see that? We have the x's, we have the z's. We're not even, it's like we're not even going to talk about y. And then the v's, all right? Those will be the velocity vectors, and in those cases, those will be the speeds, right? That's a lowercase v, okay? And then times. Now, and these can grow, right? But that doesn't necessarily mean we're not keep track. Like from time step to time step, though, it's probably a good idea to keep track of position, right? Well, we are with the x's and the z's, and it's probably a good idea to keep track of velocity, not just speed, right? From time step to time step. Okay, so we're going to go ahead through here, and we're going to define our RW, right? This is the location of some point on the wall. And this is theta, this is the slope of the ground in degrees. And there's going to be a normal vector. So in this case, theta is equal to 0. This is going to be horizontal. And RW is the location of this in space. So this has got a z. I only have a few minutes here, but let me say this. This simulation is great for watching the ball bounce and just keep going, right? I can also have periodic boundary conditions where it goes through the wall and comes back around. That's great. How would you adjust or add both of these things, actually, if you had pickleball paddles? So remember, pickleball paddles, I'm not just caring about a flat wall. That's like the ground of the court. Now I have pickleball paddles that are maybe up a meter, because that's, I'm swinging like that, right? And I have 2 pickleball paddles in this case. I have one from one player and one from another player. I want the ball to go back and forth between. What would you do to this hard wall boundary condition and the hard wall boundary condition for its neighbor in order to be able to calculate or simulate a pickleball? Yes?
It wouldn't just be like a reflection. Like it would increase off the paddle.
Yeah, so we're actually going to do pickleball in vacuum. All right? So there's going to be no drag. All right? Because I agree. Because a drag, otherwise you have to impulse, right? So this is a pickleball in vacuum, I guess I should have said. This simulation is not pickleball in vacuum, or not in vacuum. This one has drag, right? So you brought up a good point. We're going to get rid of the drag. Okay? This is the hardest thing in this problem that is your post-lab exercise. How do you define the pickleball paddles? Yes?
It's not just like a flat
Good?
thing that goes on forever. It's a contained thing that's on that.
Yes.
So far.
All right, so let's say I'm like a clown and I'm juggling, right? I don't know. But I just like have this, I'm in a vacuum, I'm a clown. Okay, let's not use clown. I am something in the vacuum, and I have my hands like this. Let's say I put them at 45 degrees, right? Now, the ball comes in, and this is like an infinite paddle, right? So there's some other impractical aspects of it, right? So the ball might come, hit my paddle here, bounce up, and over to this paddle here, and then bounce back over. Okay? You got it? So, what do I need? I need 2 paddles. I need them to be placed X distances away from each other. Right now, this is at 0. So maybe I go to like 7 meters one direction and minus 7 meters the other direction. Maybe. Okay? And maybe I change theta so that it's 45 degrees on one side and it's negative 45 degrees over here. Okay? You get what we're saying? Those are the types of changes that we're going to make pickleball happen. All right? And you'll have some parameters if you look at the post-lab exercise. Yes, someone pointed out very astutely that you're going to get rid of drag in the relay, and it comes in twice. Before I do attendance, I just want you to see, or while I do attendance, get it ready. I just want you to see what happens. So you see this? The ball is bouncing, and there's no drag in this one. I'm sorry, there's no drag in this one because it bounces all the way up to its original height. Okay? All right, and it keeps going. If I have a periodic boundary condition, okay, it'll keep bouncing around and around and around. Okay? What happened? Oh no, it didn't like that. Nope, it's because, okay, something's wrong. And then if I'm doing pickleball, it should look something like that. Okay, so it's bouncing around. Okay, so that's kind of what you're aiming to have happen. Here we go with the attendance.